I'm Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is Santa Claus. We'll look at some of the Christmas-related ideas in the fun book, The Indisputable Existence of Santa Claus. Given the book's title, we should go ahead and prove that Santa Claus exists. Here are two statements. Statement 1, statements 1 and 2 are both false. Statement 2, Santa Claus exists. Statement 1 is either true or false. First possibility is that it's true. But if statement 1 is true, then it would be true that statement 1 is false. That's a contradiction, so we have to dismiss the possibility that statement 1 is true. If statement 1 is not true, case 2, it's false. For a statement of the form both are false to be false, at least one of the parts must be true. Since statement 1 is not true, that makes statement 2 the one that is true. Santa Claus exists. So, what's wrong with this proof? One large clue is that we could have changed statement 2 to anything and still concluded that statement 2 is true. The problem is in the logic, and it's here. Self-referential statements can be neither true nor false. The classic example of this statement is false. If it's true, it's false. If it's false, it's true. So we started off with a bad assumption that statement 1 is either true or false. Then in case 1, there is no contradiction. A statement does not have to be true or false. There is a case 3, statement 1 is neither, which gives us no information about jolly old St. Nicholas. So what else do authors Fry and Evans have for us? There are some physics arguments, such as how Santa could handle all of those calories from the cookies and milk left out for him, a weighty issue. Here's a question about decorating the tree. If you want to wrap a garland around your 6-foot-tall tree, making 4 complete revolutions, how long does the garland need to be? It turns out to be an easy problem if your tree is a cylinder, say of radius 2 feet. As a sidebar, my son was given a similar problem in a middle school math counts contest. See the episode Math Counts. The trick is to unwrap the tree to make a rectangle that is 6 feet tall and some amount wide, with the garland being the diagonal/hypotenuse. The width for one wrap of the garland is the circumference of the circle, 2 pi r, which will be 4 pi. The height of that section of garland is 6 over 4, making the diagonal length the square root of 6 over 4 squared plus 4 pi squared. Multiply by 4 to get the total length. The general solution is shown. I love the visual of unwrapping the tree to get the length. Of course, this answer is only for a cylindrical Christmas tree, not typical. If you want the calculation for a more realistic shape of a cone, it's in the book. Another problem tackled in the book concerns buying or not buying a present for a new friend. If they're going to buy you one, of course you want to reciprocate. But if they're not going to buy you one, you don't want to spend the time or money to get one for them, possibly overstepping the bounds of the relationship. What you should do depends on what they do, and vice versa. Does this sound familiar? It is essentially the same as the prisoner's dilemma. See the episode Prisoner's Dilemma, which can be resolved with a tit-for-tat strategy over several years. That is, if they bought you a present last year, you buy one for them this year. And after an awkward first couple of years, the two of you agree to do the same thing. If you do buy the present, there's the problem of wrapping it and wasting all of that paper trying to make nice edges. It turns out that using a rectangular piece of wrapping paper to wrap a rectangular 3-dimensional box is not easy. Some calculations of how much paper is wasted highlight the complicated geometry of the problem. And then there's a chapter on Monopoly. Why Monopoly? As the book explains, rather than fill your special family evening debating politics or dodging prying questions about your love life, many of us turn to board games as a simple and polite way to avoid actually having to speak to each other. Sorry I asked. My favorite Monopoly game ever actually was a family event with 3 generations playing. An uncle took charge and kept everything stirred up with caucuses and trades designed to keep everybody in the game. The main Monopoly question is, which property is the best? Boardwalk and Park Place are the most expensive, but you can wait a long time before somebody lands on one of them. So how do you compute the probability that someone will land on a given property? Because of the community chest and chance cards and rules for getting out of jail, some places are more likely than others. You can compute these using a transition matrix. For a simple example of this, suppose that your game only had 4 squares, labeled A, B, C, D, and your die just the numbers 1 and 2. If you start on A, you will end up on either B or C, each with probability 1/2. The first row of your transition matrix would then be 0, 1/2, 1/2, 0. From B, you end up at C or D with equal probability, so the second row is 0, 0, 1/2, 1/2. Starting at C sends you to D or A. Row 3 is 1/2, 0, 0, 1/2, and the last row is 1/2, 1/2, 0, 0. By applying this matrix multiple times, you can get the probability of being in a location after 2 rolls, or 3, or 4, or infinity. The matrix for Monopoly is different due to having more sites and the probabilities being unequal. With 2 die, you're more likely to get a 7 than a 2, plus rolling a double in some rules means you go again. So you'll need to work hard to get the matrix in the Santa Claus book. But once you have the matrix, a relatively simple calculation called matrix multiplication lets you see where you'll end up after 2 rolls, 3, or many. If you're familiar with matrix multiplication and think it's unnecessarily convoluted, you should know that that operation is defined precisely to give these probabilities. And many rolls tells you the overall likelihood of landing on properties. The leader, drum roll please, is jail, followed by Illinois Avenue. Of course, the better question is which property will make you the most money. If you make $1,500 from an opponent landing on your Park Place hotel, but they only land there 2% of the time, your expected profit per opponent roll is 2% of $1,500. 0.02 times $1,500, $30. By this measure, the best property is Boardwalk. No surprise. But that calculation is based on the probabilities from an infinite number of rolls. Maybe in a real, finite, though it may not seem like it, finite game there are better properties. This is explored too. Boardwalk is the best, starting at about 30 opponent rolls. But that's after you get a hotel put up. In terms of sets, the book ranks them in a near tie at the top, with red, yellow, orange, followed by navy blue. So there are a lot of ways to answer the question of which property is best. Well, having put up the tree, bought the presents, cooked the turkey, there's a chapter on that too, and finished the Monopoly game, it's time to wrap up another Christmas. Pun intended, of course. I bet Christmas is more mathematical than you thought. And by the way, if you want more details on Monopoly calculations, my friend Dave Taylor has a chapter on board games in his excellent book, The Mathematics of Games. Well, Merry Christmas to all, and to all a good night.